What's going on, guys? Welcome back to another video, and in today's video we'll be going over big O notation. Big O notation is a form of algorithmic complexity, which is a concept used to represent the speed of a program. In almost all cases, the speed of a program is dependent on the number of elements involved. However, not all algorithms have the same runtimes or the same speed for the number of elements involved. For example, say we had a list of 5 elements. If we wanted to traverse this list one by one, this would be faster than traversing a list of 5,000 elements one by one. This example is what we call a linear search, and it runs in what we call big O of n, because the number of elements involved is directly proportional to the speed of the program. So this is basically a linear function. If we go back to our algebra days and graphing linear functions, it'll just be a straight line. All right. It is important to note that big O always considers the worst case scenario. For example, if we had a list of 1,000 elements, theoretically, the element we're looking for could be the first element in the list, so it could only take one try to find the element. Conversely, it could also be the last element in the list, so it could take 1,000 tries to find it. So big O always consider the worst case scenario. In this case, the worst case scenario is the fact that the element is the last item in the list. So this would be big O of 1,000, or big O of n would equal big O of 1,000, okay? Another algorithm is a binary search. We actually did a video on this. A binary search is faster than a linear search because it repeatedly divides the list in half each time we look for the element we want. Now, a binary search runs in big O of log of n, and specifically this has base 2, so big O of log of n with base 2. A list of 16 elements, for example, the maximum amount of tries it would take to find the number we're looking for is 4. And if we had a list of 32 elements, the maximum number of tries it would take would be 5, and so on. The reason this is faster than a linear search is because the more elements we have, the less amount of steps it takes. So if we had a list of 32 elements, for example, a linear search, it would take 32 tries or 32 steps. In big O notation, for a binary search, it will only take 5. Okay? Onto some other runtimes. The most efficient algorithm you can have runs in big O of 1 or big O to any constant. The reason is because this algorithm runs at the same speed regardless of how many elements there are. So whether you have a list of 1 element or 1 trillion elements, the algorithm will always be the same. So an example of this is if we had an index of a list or any type of array, if we had the index, we could always just get the number regardless of how many elements there are. So that's an example of big O of a constant, and this is the fastest algorithm possible. We also have big O of n squared. This is a quadratic function, so it's shaped like a parabola. This is slower than all the functions we've talked about so far, but typically this will be expressed as a double for loop. So a double for loop is normally run in big O of n squared. We also have big O of a constant to the power of n. So for example, if we have 100 elements, this could be big O of 3 to the 100th, for example, just some random number. And this is really slow, it's really bad. But even worse than that is big O of n factorial. This is basically the worst algorithm you could possibly write. I actually know a professor who did do this one time. You don't want to do it. It's really slow. It's going to take forever, trust me. And yeah, those are some basic algorithms that we talk about when discussing big O. Another important note is that big O focuses on the larger sets of data. So we're talking about hundreds of billions and trillions of elements, really as we approach infinity. We're not really concerned with smaller sets of data. So theoretically, a linear search algorithm could be more efficient than a logarithmic algorithm. But big O doesn't really care about that. We care about how an algorithm's performance is relative to the number of elements approaching infinity. So let's actually take a look at this. So here we have two functions. We have y equals log of x, and we have y equals x. So the first one is a log function, the second one is a linear function. Now you can see the base functions. The logarithmic function is faster than the linear function. Say we have the x-axis here. The x-axis is the number of elements, and the y-axis is the runtime, so how fast the program is. The logarithmic function will always be faster. However, if we add constants to these values, a linear algorithm could be faster than a logarithmic algorithm. For example, here, the linear function is faster for smaller sets of data. However, over time, eventually the log function will be faster than the linear function. And so when we're concerned about large sets of data, the log function will mathematically always be faster than a linear function because linear function's derivative is constant. However, a log's derivative is decreasing. So it will always surpass the linear function. This is big O notation. That's basically it. And if you enjoyed the video, make sure to like, comment, and subscribe. And I hope to see you in the next one. Take it easy.